Hello everyone, I am Sourabh Gothe. Today I will be presenting our work on unsupervised generic event boundary detection using motion cues. This work is done at Samsung Research, Bangalore, India. This is the agenda for today's presentation. Let's get started with the introduction. Shaw et al. Introduced a novel task called as generic event boundary detection or GEBD. The aim of this task is to identify the taxonomy-free event boundaries from the videos. For example, in this frame sequence, there's a change in action from running to jumping. So this constitutes a boundary. And in this sample, there's a change in illumination or environment. In this particular example, the new subject enters the scene, change in subject. Though these videos are not specific to any class of actions or events, there are boundaries which segment the video into multiple events. Hence, this is called as a generic event boundary detection. So it will also released a vast benchmark dataset called as Kinetics-GEBD, which consists more than 50,000 videos. GEBD enables several applications like video editing, summarization, keyframe selection, and many more new use cases for the end users. Mathematically, GEBD maps the ordered sequence of L frames to a set of timestamps B1 to Bm that denote the event boundaries. So GEBD is mainly solved into three approaches. Supervised approaches, where each frame is classified as boundary or not. Mainly these methods utilize the self-similarity matrix and propose to decode that representation which is generated from the frame features. In unsupervised methods, clustering of similar frames in temporal dimension is used to segment the event. In self-supervised methods, representation learning is explored and detecting spatial and temporal differences via motion are employed. We explore two pivotal questions. The first one is, can an algorithmic method, which does not require any label data for any training, outperform the unsupervised parametric or neural methods? And the second question is motion information enough to achieve the high performance? We seek to these answers by experimenting with the flow-based methods, and we present the FlowGEBD algorithm. These are the prior works. The first one is the state of the art in supervised approach, and they use structured contextual transformer in decoder and ensemble 11 such models to achieve the highest result. These two are the unsupervised methods. The first one is the current state of the art method in unsupervised GPD. They propose contrastive kernel with recursive TSM parsing and achieve the best results. The third one is the COSEC framework, which exploits a transformer-based feature reconstruction scheme to detect the event boundaries. However, in the current literature, an algorithmic approach utilizing motion information alone is not explored. We present a non-parametric algorithmic approach for unsupervised GPD that does not require any training or labeled data and yet achieves state-of-the-art performance in unsupervised tasks. So, we introduce FlowGEBD, an unsupervised algorithmic approach for GPD. FlowGEBD comprises two independent algorithms, pixel tracking and flow normalization. Pixel tracking method that relies on a sparse optical flow in temporal dimension, and the flow normalization method that traces the max temporal flow using the dense optical flow. Firstly, we divide each frame into patches spatially. There are two kinds of patches. One is regular patches or base patches, which is marked in the orange color, which is NW cross NH. And the other one is the centroidal patches, which covers the region where the base patches coincide or overlap. So with this patch-wise processing, the both algorithms can work both patch-wise and frame-wise. In fact, frame-wise is the special case of patch-wise. Before we see the exact algorithms, we can see that there's an intuition behind these algorithms. So in pixel tracking, we first sample n pixels using random sampling or the corner detection. Then we track them by identifying their motion in the next frame. If we are able to find its position in the next frame, we continue to track it further. So in the cases where there's an environment change, short change, or subject change, naturally we can expect there's a drop in the pixels that we are tracking. We cannot retain them anymore. So the hypothesis is if there's a significant drop in the pixels that we are tracking beyond certain threshold, we mark it as a boundary. And as the hypothesis holds good, where we can see that the green lines, which are ground truth boundaries, are perfectly coinciding with the drop in the pixels. The second algorithm is flow normalization. So here the intuition is for change in action, change in object of interaction, we propose that the boundaries are near to where there's a peak motion is happening when normalized over the temporal dimension. When we normalize the dense optical flow over temporal dimension and see there's a peak, these peaks are perfectly coinciding with the ground truth boundaries. So these are the intuition behind the both of the algorithms. So our FlowGEBD consists PT and FM in a parallel track, and the boundaries that are predicted from the both algorithms are passed to a temporal refinement algorithm, which removes all the redundant boundaries and provides us with the final set of event boundaries. So this is the algorithm that we propose, FlowGEBD. In pixel tracking, we first sample the n pixels from the frame 1. Then we iterate through each frame and we count the number of pixels that we can retain after calculating its flow. If this particular count is less than a certain threshold that we are no longer able to retain the pixels below certain value, then we mark it as a boundary. Then we finally send it to a refinement. Similarly, in flow normalization, this is shown in a patch-wise mode. For each patches, we calculate the dense flow and take the max of that patch. Now, we normalize this across the temporal dimension. And then, if a particular flow is more than certain threshold, then we mark it as a boundary. Then finally, we combine the set of boundaries predicted from both methods and send it to a refinement algorithm. In refinement algorithm, we basically detect a cluster of boundaries, then pick the median of that cluster as a final boundary. So this refines all the boundaries and provides the final set of boundaries. Let's go to experiments and results. So here we can see that we achieve the highest F1 score for Kinetics-GEBD and TAPOS dataset with our ensembled method compared to the other unsupervised methods. And also our method achieves the lowest inference time on the CPU. And it can also be accelerated using GPU supported optical flow estimation. So this is the overview of our results. We achieved the highest F1 score compared to other unsupervised methods, and it even surpasses the supervised baseline, which is a parametric neural method. We conducted several ablation studies where we can see that there's an increment trend with random sampling and spatial processing of base and centroidal patches. We also experimented with several patch sizes, and 5 seems to be the final or the performance highest where we achieved. The right hand side, we can see that there is a sensitivity test of the thresholds that we use. This experiment is done to understand if your algorithm is sensitive to this theta 1, theta 2, and theta 3. It can be seen that pixel tracking is almost flat, so it is not sensitive to the threshold that we choose. And in case of flow normalization, it is obvious that when we increase the maximum flow that we are seeing, the number of boundaries will decrease. So ideal cases, it's less than 0.3 is the maximum flow that you can see, and it is almost flat in that region. And in case of ensemble, it is almost flat and it achieves the best F1 score when combined. With this, I conclude my presentation with the summary. We introduced FlowGEBD, a non-parametric unsupervised approach for GBD. It comprises of 2 algorithms, pixel tracking and flow normalization, which can be deployed frame-wise or patch-wise in any edge device with the lowest inference time and no memory constraint. So we achieve state-of-the-art result in unsupervised approach in both Kinetics-GEBD and TAPOS dataset. So these are some of the references. With this, I thank you everyone. Thanks.